Hey guys, Billy Iacovelli and I were looking at the drop stones method, and we made a different version of it. So I wanted to share it with you just in case you were interested. So I renamed this Drop Stones 2D because this was using a two-dimensional array where one side was the computer and one side was the human. But we also made a 1D board. And actually, let me bring the physical board over. And so another way that we could represent this board is with one long array where the first seven elements are the player side and the last seven elements are the computer side. And we found it's actually pretty advantageous to do this. It really simplifies a lot of the code. So let me show you how this looks different in our 1D method. So the first thing is all we need as a parameter is the pit index, because presumably if you are picking a pit index that is in the first six elements of the array, or the first six indices, so 0 through 6, you're the player. Otherwise, you must be the computer. So we said, let's just keep track of whose turn it is. We made a Boolean variable to do that. And if the pit index is greater than or equal to 7, you must not be the player, you must be the computer. All right, and that'll come back in a moment. It's really going to be the thing we use to keep track of whether we skip a store. This looks almost exactly the same, except now we're only a one-dimensional array. So whatever pit what we started with, we make the stones equal to the number of that pit. We make that pit empty, and while we have stones left, we keep going. We index the pit each time. All right, now here's where it's a little bit different, but actually I think simpler. If it's the player's turn and the pit index is 13, so that would mean if we started off as the player, I started dropping stones, I get to the 13th pit. That is the computer's store. So I don't drop there. I'm just going to skip it. So we just index again and go to the next pit, which in this case would be our wraparound. Another way to think about it is if it's not the player's turn, that means it's the computer's turn. And if the pit index is 6, that's the human store, we skip it. So imagine I took this 10 here, I went 1, 2, 3, 4, 5, 6, 7, 8, skip 9, 10. So I wouldn't drop it there. So the way that we skip is we just say add to our index. This next thing is very similar. If my pit index is greater than the length of my board, it means I've gone off the edge. I need to wrap around, so put my pit index back to 0, and then go to the whatever pit I'm at, add a stone, and subtract one from my hand. Very, very, very simple. The only thing that would be really different is we're going to need to make a new display board as well. So let's try that. So we're going to do display a 1D board. And well, actually, I'm going to leave most of this here. So the first thing we're going to do is say, let's print backwards from the second half of the board. So we're going to say board dot board 1D dot length -1. That's the last index. While I is greater than board 1D dot length divided by 2, I minus minus, print out board 1D I. And then we just put a print line in here to separate it, then start at 0, board dot length divided by 2, I plus plus board 1D I. That's it. And then we pick this out. That was something else we were doing. Now, the only thing we probably need to check for an off by 1 error here. I'm not sure if this is going to be a board dot length divided by 2 plus 1 or minus 1. But off by 1 errors are easy to fix. You display it, you see what happens. I think what we have here is we made there's our two-dimensional board. Let's make our one-dimensional board. Board 1D equals a new int array that's going to be 14. And then we can just do, actually, this will be one long for loop for int I equals 0, I is less than board 1D dot length. And really, we're going to do a minus 1. Let's get that last store. I plus plus. And we're going to do a board. Oh, I had to do an if in here. If I does not equal 6. Actually, we want to skip that store. Board 1D equals 4. There's our filled 1D board. All right, so we initialized the 1D board, we filled the 1D board, and I know we didn't actually write that method, so let's take this out. Pit num, we'll call it, let's say, pit 4. I'm going to comment out some of this stuff, actually, just to see how this looks. So let's do display our 1D board. And then we're going to do a drop stones 1D. Pit num, we'll take the third pit. So we'll do pit 3, and then we'll display the 1D board again. Let's see how this works, if it works. Oh, that didn't work at all. I think our display may be off. Let's see. Display 1D board, board dot length minus 1 divided by or greater than or equal to that. That part looks fine. And then start at 0. Oh, board 1D. There we go. Hey, look at that. There's our 1D board printed out all nice. And there is our player taking their pit number 3, 1, 2, 3, 4, dropping the stones. Wraparound works. Let's try having the computer do one with a wraparound. So that would be, let's say, be 7 or 6, 7, 8, 9, 10. Let's do pit 11. So that should be this guy right here. And run it again. Look at that. Works both directions. All right, so there's the 1D version. And again, this is the same for Python as for Java. We're just doing the logic here. So we have our two-dimensional array. So if we are storing each side as an individual array, here's a way to drop the stones on a 2D array. Here's a way to drop stones on a 1D array. The benefit to both of these is they're very scalable. If I was to say, you know what, make a Mancala board that has 20 pits per side, make a Mancala board that has 8 players, both of these can scale very well because most of our logic is a mathematical operation rather than lots of if statements. But just wanted to share that with you. I'll see you guys. Bye.